In this video, we're going to look at stoichiometry and gases and how a really interesting feature about gases will allow us to do particular types of stoichiometric calculations that solids and solutions will not allow us to do. And that feature is the fact that if you have the same, a particular same volume of gases, and the pressure and temperature are held constant, you'll have the same number of molecules in that volume. So no matter what the gas is, as long as the pressure and temperature are held constant, that volume you have will have this of one gas will have the same number of molecules in that volume as if in the other gas at that same volume. And so because that is true, we can use in a balanced chemical equation of gases the coefficients as just a stoichiometric factor in order to convert from volume to volume of substances. So in this particular equation that you see down here, where you have nitrogen reacting with hydrogen gas to produce ammonia gas, what this balanced equation of 1 to 3 to 2 suggests is that for every 1 volume of N2, you will react 3 volumes of H2 to produce 2 volumes of NH3. And so when I say volumes, that unit can be whatever units you want, if that's liters versus milliliters versus quarts, if you will. So that volume is kind of ubiquitous. It's just as long as it's the same unit. So let's use this aspect to calculate or solve for a particular example. So it says an acetylene tank of an oxyacetylene welding torch provides 9,340 liters of acetylene gas, which is C2H2, at 0 degrees C and 1 atm. And how many tanks of oxygen, each of them having 7.00 times 10 to the third liters of oxygen at that same temperature and pressure of 0 degrees C and 1 atm, will be required to burn all of the acetylene in this tank of 9,340 liters. So essentially what we're going to do is we're starting with 7.00 times 10 to the third liters of O2, and we're going to try to find stoichiometrically what volume of acetylene is used to react with all of that oxygen in that tank, and then how many tanks would it take to react with all of the 9,340 liters of acetylene. And so to do this, we just use the stoichiometric factors of to volume in conversion. So we can do 7.00 times 10 to the third liters of O2, and the stoichiometric factor of 5 liters of O2 to 2 liters of C2H2 will give you how much volume you need of acetylene to actually react with all of that oxygen. So it ends up being 2,800 liters of C2H2, and if you're wanting to put that in the proper sig figs, 2.80 times 10 to the third liters would be that value. And so now that we have that, we're going to take that and divide that value into the total amount of acetylene we have in that acetylene tank. And so we're going to divide 2.80 times 10 to the third liters of how much is needed to react with oxygen. And that will give us a value to 3 significant figures of 3.34 tanks of O2. So this is how you would use that process of that volume stoichiometry in a balanced chemical reaction. Keep in mind that this is only usable if you're at the same temperature and pressure. So if you are not at that, then there would be some different things that you would have to do, like maybe use the combined gas law to adjust one volume into the same temperature and pressure used in another value. Okay, so let's do this again with another problem, except this problem we're going to use some stoichiometry that has mass instead of volume. And so the example question number 2 asks, what volume of oxygen at 423.0 Kelvin and a pressure of 127.4 kilopascals is produced by the decomposition of 129.7 grams of Ba2 to BaO and O2. So that chemical reaction is written here that you can see. And it's saying essentially if we have 129.7 grams of this, what volume of that will be of oxygen will be produced if this is the temperature and the pressure. And so there's a couple of ways to do this. And I think the easiest way is let's use the ideal gas law. So PV equals nRT, meaning, hey, if we know the pressure here, we know the temperature from here, and we know the R value, we give that constant, and we're asking for what's the volume. The only thing we need to solve for using this stoichiometry here is the number of moles of O2. And so that's a really easy problem. We've learned how to do that in many, many chapters and previous in this course. And so let's do that really quick. So if you start with 129.7 grams of BaO2, and we're going to convert that to moles of BaO2. We're going to use its molar mass of 169.30 grams of BaO2 is equivalent to 1 mole BaO2. And then we're going to use stoichiometry. For every 1 mole of it, it's equal to 1 mole of oxygen. So for 1 mole of BaO2, that's equal to, sorry, for every 2 moles, it's equal to 1 mole of O2. And that'll give us a value for 6 figs of 0.3830 moles of O2. Well, now, guess what? We can plug that right into there and we can solve for volume. So our volume equals our moles times constant times temperature divided by pressure. And those values are as such: 0.3830 moles times, and let's look at what our R should be. Since our pressure is in kilopascals, we're going to use the 8.314 liters kilopascals divided by mole Kelvin. Our temperature is already in Kelvin, so 423.0 Kelvin, divided by our pressure of 127.4 kilopascals. Let me redraw that line real quick. There we go. And so now we'll plug this into our calculator. Before you do that, just check your units really quick. Kilopascals cancel. Kelvin, moles leaves us with liters, which is we're trying to calculate volume, so that's good. And I get a value of plugging all this in, solving for 4 sig figs of 10.57 liters. And that's how many liters of oxygen you will make in that reaction. Okay, so this is a video that we have looked at stoichiometry that has included gas pressures and how we could use volumes also as a stoichiometric factor.